Hello everyone, Mini Motorman here, and today what we're going to be exploring is the question, why do motorcycles get bad fuel economy? Now, being a motorcycle rider and fan and mechanic of many years, there's been a question I had for a very long time about these two-wheelers. You see, if you're familiar with motorcycles, you might realize that while you can save a bit of fuel compared to a car, that is, for example, the R6 I used to ride did 45 miles per gallon, while the V6 Ford I drove did, at best, 26. But when comparing the average fuel economy of many motorcycles versus a vast array of cars, you quickly begin to see a pattern. Of course, cars and motorcycles come in all sorts of shapes, sizes, powers, and price tags, but for the sake of comparison, I'll be looking at a basic set of commuter motorcycles such as the Kawasaki Ninja 300, Honda CBR 300, Yamaha R3, and Vespa GTS 300, and various 3-litre petrol V6 cars such as VW's 2.8 VR6 powered Passat, Nissan's VQ30 powered Gen 5 Maxima, Mitsubishi's 6G72 Galant, and Toyota's 1MZ XV20 Camry. And the reason I list these cars is because I'm somewhat familiar with their engines and because they're roughly 3 litres, or roughly 10 times the displacement of the 300cc motorcycles, and you'll see why I use that comparison in a short bit. Now, if we take a look at the fuel economy estimates of the Ninja 300, CBR 300, R3 and GTS 300, we will see the following. And if we look at the fuel economy estimates for the Passat, Maxima, Galant and Camry, we see the following. So besides the R3 being the odd one out, the 300 class of bikes seem to average roughly mid-80s when it comes to fuel economy in miles per gallon. And keep in mind, these are estimates. So I wouldn't be surprised if the R3 in fact kept pace with the group, given that it is very similar to power output and performance as the Ninja 300. And then moving on to cars, we can see the story again is roughly the same. All cars for the most part averaging 24 to 26 miles per gallon. But one thing that might strike you, as it did to me all those years ago, is how come a 300cc motorcycle only does just over 3 times the fuel economy of a 3000cc displacement car? If displacement is anything to go by, then shouldn't the 300cc motorcycles be doing 10 times the fuel economy? And what about 50cc scooters? Why are they only estimated at 130 to 140 miles per gallon and not 60 times the 3-litre cars? Because they're 1/60th the displacement, which would be 1500 miles per gallon. Now, searching books and online conjectures, I've heard many explanations from motorcycles are less aerodynamic, to motorcycles rev higher, to motorcycles have over-square engines and are therefore less efficient, to the simple motorcycles are just ridden harder arguments. But as I dove into each and every one of these, they still didn't fully answer the question. While yes, motorcycles have much worse drag coefficients than cars, even a sport bike like the R6 I used to ride I've seen quoted at a 0.6 drag coefficient figure, and that is supposedly with an aerodynamic helmet and being in the fully crouched over position. That still didn't explain the 42 miles a gallon I would average while riding in town at speeds when aerodynamics played very little part, which consequently was only slightly less mileage than I was getting than my much bigger and heavier Suzuki hatchback. Of course, you could explain the R6's fuel consumption down to the high revs it was consistently at. But then when you look at the Harley-Davidson 883, for example, and the fuel mileage in town roughly stays the same despite the low revs and similar displacement motor as my Suzuki, then the rev higher and over-square engine arguments go out the window as well. Now, you could simply say that Harleys must be rubbish motorcycles, but looking at similarly proportioned Honda Shadow 750s, that argument doesn't seem to hold much weight either. And when it comes to motorcycles being ridden harder, I suppose this might be subjectively true given that riding a relatively lazy-feeling Sportster is loads more fun than a much less interesting four-door Suzuki, but if that were the case that all motorcycles simply got worse fuel economy than cars because riders were simply reckless knobs, then we'd be led to believe that if someone wanted to, there would be a secret hack, if you will, to using a motorcycle as a mode of transportation, and that somehow triple-digit fuel economies could be had if you could simply keep your hand off the throttle. But given that I've ridden motorcycles for almost 20 years now, Much of those years as my primary mode of transportation, I can assure you that no such hack exists. I've ridden 200 horsepower rockets to 5 horsepower scooters, and I have never once cracked 1,000, 500, or even 200 miles per gallon with everyday riding on anything on the plus side of 125 cc's. Best I've been able to average is around 155 miles per gallon with my Super Cub 50 that I currently have, and that is with an average speed of 22 miles per hour, so needless to say it only works in a very crowded city with slow traffic. And even with my slow and low revving 250s, I'd struggle to break 90 miles per gallon even on a good day. So what's the deal then? If none of those statements appear to be singularly responsible for motorcycles' poor fuel economy in general, then what is? Well, I'll let you in on a hint. The problem here is not with the motorcycles themselves, but with the question we are asking. The question isn't, why do motorcycles get bad fuel economy? The question should be phrased, why do we think motorcycles get bad fuel economy? Well, if we look at how I presume most people view motorcycles compared to cars, I think we'll find a clue on the beginning to understanding why. Firstly, when I asked this question to myself when I was younger, I was looking at mainly two things when comparing motorcycle fuel economy to a car's fuel economy, and that was the engine size and the weight. Makes sense, right? The engine is what burns fuel, and the weight represents the thing you're moving with said engine. So when comparing a Honda CBR 300 to an Accord V6, it would seem logical that the 300cc motorcycle would get roughly 10 times the fuel economy of the 3000cc car at a cruise, where weight doesn't come much into play, and roughly 6 times the fuel economy in the city because a 500-pound motorcycle, 130-pound rider included, is around a sixth of the weight of a 3,000-pound car. So if the Accord's fuel economy is estimated at a 22 mile per gallon urban driving and 31 mile per gallon in extra urban circumstances, then the CBR 300's fuel economy would, according to this logic, look like this. But having ridden a modern 300 as a commuter for a short while, I can tell you that while indeed this sounds nice in theory, it is completely wrong. Expect 70 to 75 miles per gallon in the city and 85 to 90 miles per gallon while cruising at a light 30 to 40 miles per hour. Now, while no one would complain with that kind of fuel economy, and rarely does anyone ever do, it still begs the question, is there something wrong with motorcycles? Or is it a problem with our question? As stated, the problem is actually with our question. So assuming then that motorcycles in fact are well engineered and very fuel efficient vehicles from the get-go, and that there isn't some massive global conspiracy by oil companies to keep the little fuel sippers like this from reaching that mythical 300 mile per gallon mark, let's take a look now as to why this conspiracy theory doesn't exist. To understand this, first what we are going to do is break up fuel economy into two separate figures in order to understand both city and motorway ratings, or urban and extra-urban ratings. So first, instead of looking at the displacement to determine the fuel consumption of an engine, we need to look at a different figure less well known and often not found on any spec sheet of any motorcycle or car, but one that commercial equipment people will know oftentimes very well. That figure is called BSFC, or Brake Specific Fuel Consumption, which basically is a measure of how much physical fuel is burned per unit of power harnessed. People like to use the term power being generated when it comes to engines, but I personally don't like to because it's incorrect, although I will probably digress at times just to let you know. You see, the engine is not responsible for making or producing anything. It is taking something with power already in it, the fuel, and then releasing that energy in the fuel and attempting to capture as much of that energy as possible so it can turn it into rotational motion. So the term BSFC quantifies just how much fuel gets turned into motion, which, if you're into efficiencies of motors, is the figure often sought after by hypermilers and eco-modders when it comes to finding a suitable vehicle for high fuel economy challenges or for personal modification. So to apply this to the real world now, let's assume for the sake of simplicity that we have two vehicles. a car with a 30% efficient engine, and a motorcycle with a 30% efficient engine. Now let's do some maths. And to start with, we are only going to look at motorway fuel economy, as it is the easiest to understand at first, and then we will move on to city fuel economy. Now what we'll do is open up an aerodynamic drag calculator, which calculates how much horsepower is needed based on frontal area, the drag coefficient, weight, and speed of a vehicle. Basically, it tells you how much power you need to push something through the wind at any given speed. So if we plug in the Mondeo's dimensions, we'll see that roughly 27 horsepower is required, assuming the car is 3,500 pounds, has a frontal area of 29.36 square feet, a drag coefficient of 0.3, and traveling at a motorway speed of 70 miles per hour. And then if we plug in, say, a typical motorcycle's dimensions, we'll see that roughly 14.6 horsepower is required, assuming the motorcycle is 500 pounds, takes up 10 square feet of frontal area, has a drag coefficient of 0.6, which was that of the R6, and is also traveling at 70 miles per hour. Now, assuming both engines are 30% efficient at this power requirement, let's calculate the fuel consumption. If we were to drive at 70 miles per hour, and it requires 27 horsepower to do so, we would need to consume 27 horsepower hours of fuel, which means for petrol, 12.5 pounds or 1.62 gallons, given that petrol is roughly 7.5 pounds per imperial gallon. If you divide the 70 miles we would travel in that hour, 70 miles per hour, and divide that by 1.62 gallons of fuel used, we would end up with a 43.2 mile per gallon figure. This seems to be relatively in line as seen here for fuel economy. Now, if we were to take the motorcycle's requirement of 14.6 horsepower and assume the engine is also 30% efficient, which is a bit high to be honest, but no matter, let's just continue for the sake of simplicity, then the motor would need to consume 0.88 gallons. Taking that same 70 miles per hour and dividing it by 0.88 gallons, and we get 79.5 miles per gallon. Hey, fancy that? That's right around the ballpark of what we were to expect by the maths alone. If you think about it, while a car may look and be much bigger than a motorcycle, when it comes to frontal area, they aren't as different as you might think. When you look at them head on, you can see how much space, so to speak, they actually take, and this is the only thing the wind cares about. This is why aeroplanes are built the way they are and not like this, to reduce their profile to the oncoming wind so that less fuel is required. So, there's our answer to a two-wheeler's motorway economy. But now, how does this relate to city fuel economy then? I mean, how does it make sense that a 500-pound or 600-pound motorcycle doesn't get 6 times more fuel economy than a 3,000-pound car? And the answer is actually a little more complicated than the motorway example, which is why I went to that one first, so bear with me, but I think you can understand if we walk through this together. So, going back to start with, let's look at the 30% efficient example. You'll notice that in just 1 hour, the Ford consumed 1.62 gallons of fuel, but because it was going 70 miles per hour, it covered roughly 43 miles per gallon worth of fuel consumption. So if that same Ford was going 35 miles per hour in terms of average speed, then it would consume 1 gallon of fuel because half of the power is required to keep it at this speed, right? Well, wrong actually. At half of the speed, the amount of power required is actually a quarter, because as the speed doubles, the power required exponentially increases, or roughly quadruples. So the required amount of horsepower to keep the car at a consistent 35 miles per hour is around 5.8. So 5.8 equals 0.348 gallons worth of fuel. So at 35 miles per hour, at 0.348 gallons means that we should be seeing a fuel economy of 100 miles per gallon. But that's obviously not the case, so what's going on here? First clue is going to relate to the power band of the engine, and to understand why, let's have a look at the dyno sheet for a 2-litre EcoBoost motor. Now, as you can see here, At 1500 RPMs, the engine is only making roughly 25 horsepower and nearly 100 Newton meters worth of torque, which is about 75 foot-pounds, which, may I add interestingly, is right around the ballpark area of another certain four-cylinder Ford from an earlier vintage, the Model T. In fact, having a look at some dyno test results from a Model T owners club in America, we can see some people are in fact making nearly identical figures to the modern-day Mondeo in terms of horsepower and torque, the best of which being 25 horsepower and 94 foot-pounds of torque at the same 1500 RPMs. Yes, the Model T does make use of a 2.9-litre motor and not a 2-litre, but also keep in mind the Tin Lizzie is a century older. Makes you realize how much of a genius Ford and his engineers were at designing this beast. Maybe they knew a thing or two about thermal efficiency, no? But anyway, back to the Mondeo. Now, if we look at the BSFC chart, we can see that 1500 RPMs and 100 Newton meters is actually slightly outside the green area, which for simplicity's sake means the place we want to be for max efficiency. I guess that's a song or something, but anyway, this actually seems to coincide with the US EPA rating of 37 miles per gallon versus the 43.2 miles per gallon estimate we made earlier, because remember, we're assuming the engine was running at its peak efficiency at that 70 miles per hour, but as we can see from the dyno, if the engine was putting out that approximate 25 to 27 horsepower at 1500 RPMs and that amount of torque, it would place it just outside that peak efficiency pocket. So from a numbers point of view, this seems to coincide with the 31 mile per gallon US estimate that we see on the US highway rating. And the reason I'm using the highway fuel economy rating of the US is because of the higher average speed they test the vehicles at compared to the European rating. But coupled to that the stops and acceleration runs up to 80 miles per hour for their method of testing, and the slightly lower fuel economy ratings begin to make even more sense. So, how does this relate to city driving then? Well, keep in mind that most of the figures we've been dealing with have all related to peak efficiency of an engine, which is a fixed speed an engine operates at and a fixed load. But city driving is exactly not that. To understand why, let's go back to the dyno chart. Now, the dyno doesn't go lower than 1300 RPMs, but if we look at the specific fuel consumption graph, the efficiency drops all the way to 360 grams per kilowatt hour, which, when referencing that to this table here, you can see that the efficiency percentage is all the way down to the low 20s. And when you begin to add into the mix idling and braking, efficiency numbers take an even further nosedive. So, while it may seem logical to assuming that because a car uses only a quarter of the average horsepower and therefore a quarter of the fuel for city driving, unfortunately, an engine cannot be made to run at its peak efficiency at these very low speeds. So instead of factoring a 30% efficiency in the case of the Mondeo, which would indeed mean 100 miles per gallon in the city if it could achieve this, surprisingly, we are actually closer to single digits. This means that when producing the 3 or 4 times less average horsepower hours needed to continually propel the car down the road, the Mondeo is actually using 3 to 4 times more fuel to produce that same amount of horsepower because it's so far out of its peak efficiency range. This is what happens in the case of city fuel economy. An engine is typically used at not even 1 to 2% of its peak power and torque, which is by far its least efficient area to operate in. Yes, the power demands are much less, but by the same token, the efficiency is also much less. So over the course of the same time in driving said vehicle, the engine actually consumes approximately the same amount of fuel in the city in comparison to the highway. To just make sure that you understand this, because I admit it's not really intuitive when you first think about it, let me rephrase. The average horsepower requirement of the Mondeo at a 70 mile per hour average speed is roughly 27, and the fuel economy was roughly 40 miles per gallon. Now, if we go back to the horsepower calculator and input the average speed at 35 miles per hour, then we can see the horsepower requirement is not half of 27, but less than a quarter at 5.8. This is 4.65 times less. But looking at the peak power of the Mondeo of 240 horsepower and realizing that 6 horsepower is only 2.5% of the total power the motor can produce, we can almost accurately say that the motor is practically idling. Try giving your throttle 2.5% of a push to see what I mean. And yes, I know, motors don't respond linearly to throttle inputs, but you get the general concept. It's not much. So if we have a quick look at the efficiency of a petrol engine at idle or near idle, we can see that it's not 30% efficient or even 15% efficient, but in the case of this Pratt & Whitney engine, it is a rather low 6.6% efficient, which is incidentally also less than a quarter of the 30% peak efficiency, or 4.54 times less. So if we look at the original figure of approximately 40 miles per gallon from the motorway cruising speed and multiplied it by the power requirements at 35 miles per hour, which is 4.65 times less, we would see that the fuel economy rating would then become 186 miles per gallon. But if because the motor is running in such an inefficient manner at such low power settings, roughly 4.54 times less efficient, then dividing that 186 miles per gallon figure drops right back down to 41 miles per gallon, incidentally. However, this figure does not take into account braking, idling at 0 miles per hour, using auxiliary devices such as the air conditioning, electrical accessories, warming up the engine from ambient temperature, and a whole lot of other factors, and suddenly the slightly lower than cruising speed fuel economy numbers begin to make sense. Now, as mentioned, it largely varies on how you drive in the city, how many gadgets you use, how much you use your brakes versus coasting, and how hard you accelerate. But the short answer to this is, the reason why fuel economy in the city also takes a plunge on both motorcycles and cars is because the amount of power you use from your car's or motorcycle's engine is typically such a small amount, on average, that it means your engine is running in a terribly inefficient area of its power-producing capability. As you can see with the Ford, just going from 100 Newton meters of torque to 25 Newton meters, the efficiency nearly halved and showed no signs of slowing down. And likewise, if you have a fairly powerful, in comparison, motorcycle engine, powering an even somewhat bulky 700-pound bike, for example, you're doing the exact same thing and using just a small fraction of the available horsepower your engine can produce, and as a result, your fuel economy will also suffer likewise. Of course, because a bike is so light in comparison, the city numbers aren't as drastically as low as the cars, for example, and that's why most bikes tend to be rated with one number rather than two, because the amount of momentum that is thrown away from the brakes is a lot less than a car, but still, by the same token, this is also why motorcycles don't have a sky-high city fuel economy rating, because the inefficient area they operate at in low-powered settings. Now, of course, this is the real world, however, and economy isn't the only thing we're interested in, because if it was, then ideally what we do is put a much smaller engine in our vehicles and stress that engine to the moon and hope we never need more power than its peak efficiency band can offer. But engines have a lot of little parts inside, and putting those parts under max torque and stress at all times tends to make them break, which, while might be getting slightly higher fuel efficiency numbers being under high load all the time, won't be very reliable or durable in the long run. And people tend not to like replacing their engines very often, if at all. So that is why many of the vehicles we have today are in fact severely understressed engines in comparison, because it offers greater reliability for everyday driving, a high peak power when desired for things like passing or just setting off, and also adds significantly to the comfort if you think about it. I mean, who wants to drive like this all day? But either or, I hope this was at least able to give you an idea why the question on why motorcycles get poor fuel economy is a question built on false pretenses, and also give you a greater general understanding on what fuel economy is in general. Motorcycles do not, in fact, get poor fuel economy when compared to cars. They simply get fuel economy according to the dictates of the laws of thermodynamics and physics. Nothing more and nothing less. Anyway, I'll best cut things here, otherwise I could go on all day about the subject that I'm rather fond of studying. But anyway, once again, I hope you learned something useful and that this video was helpful. I'm Mini Motorman, and until next time, goodbye.